You're on.
Hi, everybody. I'm just here to let you guys know that SAS will be holding our second exam review this coming Tuesday, October 12th from 7 to 9 p.m. It's in the same room as last time, Derlin/Fiedler, room 1107. Again, we're just going to go over an old exam, and if you guys have any extra questions afterwards, we'll be happy to stay as long as we needed to get everybody to feel comfortable and ready for this exam. Does anyone have any questions? Looks good. Okay, hope to see you guys there.
All right, thanks, Gabriel. Great. Go SAS. All right. So there is an exam next week. Thursday, same room as before that you were in. All three exams will be in the same rooms. The final will be in a different room, and I'll make that announcement when we get there. I will also have a review Wednesday evening. So review Wednesday. I have to look at my schedule, but I think it'll probably be 6 or 6:30. But I'll make the announcement next week, and I'll send an announcement on Canvas. So this is for exam 2. This morning I did post a written practice exam on the module for this week, so you can find it right before the actual exam on that module, as well as the solution set for that written practice exam. Those, I'm going to remind people, those are not for extra credit. The online practice exam is, so you should take that. And I think that should open up today if it isn't already. And so again, it's last review session. I mean, I'll say this again on Tuesday, but last review session, I did notice a lot of people were very, very active in asking questions during the review, which was great. And I really appreciated that. But it helps me a little bit to have some of those questions ahead of time so that I can kind of prepare more consciously what kind of problem I might be reviewing. And that's more to help you prepare for the exam as best I can. So if you can send me questions that you have about this material over the weekend or before the review session, that will help to make a better review session. All right. The material that's covered, of course, is written on the exam and on the exam page in Canvas, but it's all of the material up through today, including today, starting at the end of where we left off with the last exam. So there are some things from chapter 3 that we will cover the last couple of sections, 3.2.3.3, I want to say. Okay, we will talk more about this next week, but right now I want to continue moving forward and talk about section 4.6, which deals with directional derivatives and gradient. Now the gradient is the main player, I want to say. So these are not equal footing. Gradient tells us everything we want for directional derivatives and more. So the gradient is what we'll get to, but directional derivatives have a more, I think, intuitive flavor. And so let's start with them, the definition. So I'm going to do this in n dimensions. We'll, in practice, well, actually, let's just do it in 2 dimensions. Let's just start in 2 dimensions. So today we're going to do it in 2 dimensions, but you can do this in n dimensions. The generalization is very straightforward. So let's take a unit vector, u, u1, u2. And let's suppose we have a differentiable function. Actually, it doesn't even need to be differentiable. Let's just say we have a function of 2 variables, f(x, y), it's a function. I do want it defined near a point, say AB in the plane. And by near, I mean there's some open set containing AB, maybe a small open disk, for which F is defined on that open disk, at least away from AB. Then the directional derivative of F in the direction of U, pardon me, direction of U is the following quantity. Well, the notation looks a little like this total derivative, but it's quite different actually. Du F of AB. This is the notation, but what is it actually equal to? Well, it's a limit. We'll take h approaching 0, and we're going to take f of a plus h times u1, b plus h times u2, and subtract f of ab. Okay. We're going to divide that whole thing by h. So that's the definition of directional derivative. In the book, so note, in the book, they write u as cosine theta, sine theta, because of course every unit vector can be written this way for some angle theta. But you can see, I mean, well, you hopefully, looking at this definition, could see how to generalize this to 3 dimensions. And in that case, you don't want just a single angle theta. You really just want to choose a unit vector. So what is this saying? What is the idea? Well, let's see. So let's say we have our function and we want to draw a little graph of the function. So let me give myself some coordinates, some axes anyway. And let's give myself some kind of paraboloid kind of guy. Say this is my function. And this guy here. So now, let's say I've got some point down here on the XY plane, this point AB. And I can move up and see where it goes on the graph. So it goes here. So this is the graph of the function up here. So z equals f of xy. So what we're looking for, so now the one ingredient we don't have in this picture, we have our point AB, we have our function f. We don't have this unit vector u. So what we'll do is we'll look at that unit vector and consider some, say u to be, let me draw a vector here. See if it cooperates. There we go. So let's say we have this vector. We put this vector with initial point at AB, and then we have sort of several different directions we can point, depending on what we want. So let's say we're pointing over in this direction. Then we can take this line in that direction. Let's say, not that line. Hopefully we can take a line. There we go. So let's say this is moving in this direction. And then we can look at the graph over that line. So let me just sketch it. So let's say this graph is like this. It's a little shaky, it's too much coffee. And I can ask, what is the tangent, what is the rate of growth of f along that line? In other words, what's the sort of slope of this tangent in this direction? That tangent here. That slope is going to be our directional derivative. The rate of change as we move in the direction of u starting at AB, the rate of change of f. That's the idea. Is it clear, the idea? Okay. This is very useful, right? If you want, let's say let's say your function is the height of, some mountain range or whatever, and you're interested in how steep or the slope is in any given direction. You're trying to program a rover or whatever on Mars, right? You want to know sort of these rates of change in these different directions, not just a single X or Y direction that you might be going in. Of course, it is useful to note that if I take d of 1, 0 of f, this has another, I mean, I can evaluate it at AB, or I can think of it as a function. So other notation that we might be familiar with, which is maybe what? I'm sorry? F sub x. This is the first partial of f in the direction of x. Or f sub x. And if I take d 0, 1, this is del f del y. In fact, this is, if you look at the definition written up here, this is precisely the definition of these first partials for these particular unit vectors. Okay. So this is just a generalization. You can think of it as a generalization of first partials, but now we allow different directions than just the coordinate axes, and just moving parallel to coordinate axes. All right. Good. So there's a theorem. We can this theorem. All right, so if f is differentiable, which most of our functions are, at AB, and use our unit vector, then this directional derivative of f at AB is just equal to the first partial of f with respect to x at AB times u1 plus the first partial y, or f with respect to y at AB times u2. So this theorem tells us that there's a real easy way to write down the directional derivative. You don't have to take these nasty limits. You can, as long as you know your first partials with respect to x and y, and as long as your function is differentiable, you can just write it as a combination of those first partials. So it's interesting, last year, so this is a theorem in the book, it's a useful theorem. Last year I looked at the book, which I occasionally do. And everyone should do that, right? So, but this was actually incorrect in the book last year. So I had to send them a correction. I think they corrected it. But the funny thing about that story is that, I don't know if it's funny, but the thing about that story is that this is an open source text, which in some ways is very good because it keeps everybody on their toes, right? There's a lot of, every year, there are a lot of errors that get corrected. So it's gotten much better over the years, but you should always approach this text with sort of an eye of, if something's wrong, maybe there's something wrong with the text, right? So it's a good practice to be in. Sometimes I get statements like there's something wrong with this exercise, and indeed there may be something with the exercise. So if you see such things, you can always send a correction, or you can just tell your recitation instructor they can send a correction. So why is this true, though? So why is this true? So let's actually explain why this works, and then we'll apply it. Because this is a useful thing to understand, I think, why this actually works. So let's take a function g. I'm going to define this function as a plus u1 times t, b plus u2 times t. What is this function? Someone can tell me what this function is. Yes, back in the back. Huh? A line. This is a parametrization of a line. You guys remember from one, right? What's the direction vector for this parametrization of this line? I didn't write it. So you have every reason to not know. I said give myself this vector. It was written above, but let me write it down. U. U is the direction vector of this line. It's a line in the plane with direction vector U. So this line, this function is parametrizing this blue line here in the plane. Okay. At time equaling 0, we're at AB. Is it clear? Everyone agree? Bring back good memories of lines, parametric lines? Yeah, good. Everyone's happy. Okay, note that du of f of AB is equal to the derivative at t equaling 0 of f composed of g. Just note that. Go back to your high school or middle school or elementary school calculus book. Right? Go look. Definition of derivative. You'll see that this is the definition of the derivative for this function f composed of g. It is the, as we're saying, it's the rate of change as you travel along this line at speed. So what do you recognize when you see this formulation? Chain rule, I heard someone say it. I'm taking a derivative of a composition, right? And what we talked about on Tuesday is precisely how we can do that. We can take if we're taking derivatives of compositions, we can take the individual derivatives and compose them, but now we have this total derivative. We have these matrices. So let's do that. What's the total derivative? What's the total derivative of g? So d of g, this is just going to be the derivatives of each of the component functions, this function and this function. This is a vector valued function. It goes from R to R2. Its derivative, someone can tell me? It's a velocity, in this case, a vector valued function, its derivative is just the velocity vector at a particular point t. It's u, great, I heard someone say u. It's u, it's constant. It's not even dependent on t, it's just u, right? If I take the derivative of this with respect to t, I get u1. This with respect to t, I get u2. So that's u as a vector. But it is a vector. And I'll write it as a vector instead of a matrix. But you can, okay, if I wanted to write it as a matrix, maybe I'll write it that way, sorry. But we'll conflate these two things. So row vector, if you will. df, well, df is just what df is, right? It's going to be del f del x. Yeah, okay, I'm regretting this a little bit. Del f del y. Or if you want, we can do this at AB. And we can evaluate this. I'm sorry, guys, let me evaluate this at AB. fx AB, because I want to agree with the notation. Now, okay, if I was doing it as I did it last time, I think we would write this as a column vector instead of a row vector. And then we would multiply these two together. And what we would get is we would get df AB dg is equal to precisely this. This is the chain rule. So the reason why this formula holds is the chain rule. That's the point at the end of the day. Now it's funny that what I was saying last about the correction I sent into them is before they had written not differentiable, but first partials existed. It is not true then. And you can construct nice examples where this will not hold unless the function f is differentiable. So you do need that condition. All right, let's do a computational problem so that we feel comfortable with this. Suppose we have a vector u, square root of 2 over 2, negative square root of 2 over 2. And then we want to find the directional derivative of the following function. Say f xy equaling x cubed to minus 2xy plus y squared in the direction of u. Okay. Well, again, if you start out with a limit definition, you would get a solution, but it's better to use this theorem that we just went over, because of course f is a polynomial, so it's differentiable in both to arbitrary degree, really. So we just go ahead and use this theorem. So let's compute. Compute the first partials of f with respect to x. It's going to be, so it's a 3. It's going to be 3x squared minus 2y. That's f sub x. F sub y is going to be negative, well, I guess 2y minus 2x. And so if we want to calculate the directional derivative, du, and here again, just like with partials, you can evaluate that this is a function. You can write this as a function, or you can evaluate it at a point. So we'll just write it as a function. Du of f is going to be equal to, we take square root of 2 over 2, multiply fx by this, and add, well, negative square root of 2, so we subtract square root of 2 over 2, fy. Which, when we expand it out, we'll get square root of 2 over 2 times x, 3 times x squared, minus square root of 2 times y, canceling the 2's, and then subtracting, again, square root of 2 times y, and then we have plus square root of 2x. So we'll get a little simplification. 3 square root of 2 over 2 x squared minus 2 square root of 2y plus square root of 2x. All right. So not a hard computation, not a hard computation. Certainly with the theorem, not a hard computation, because we know how to take first partials. All right. So now what we'd like is we would like a vector that sort of helps us understand directional derivatives sort of all at once. And this will be sort of the first introduction to, I guess, vector fields, but we may or may not talk about them as vector fields quite yet. So this is about the gradient. Now, gradients are sort of ubiquitous things in mathematics and in applications. You'll see them as potential functions for various force fields, taking the gradient of a potential, and you see them in all sorts of applications in physics, computer science, and engineering. So I won't get into all of those. I'll let your professors in those disciplines talk about it, but we'll just talk about the math. So let's do the definition. So the gradient of f of xy, and here I do want to kind of think about also the general case. So, or let's say we have a function of several variables, x1 through xn, is the vector valued function valued function in the sense that I was talking about from my perspective and from all the rest of the math community's perspective. Vector valued functions are just functions that take values in a vector space. Also, this could be called a vector field if you wanted, but it's denoted nabla of F, nabla F, and it's equal to just the vector obtained by putting in the first partials of F into their associated coordinates or components. All right. There's other notation for this. So other notation, not as frequently used, would be what's known as grad F for gradient. I'm trying to think of others. There are probably others, but I can't think of any. Now, I want to say something which is, I don't know, controversial here. Because it's a little too far advanced, but I'm not going to spend time on it. The gradient actually, even though it looks very natural, is actually a very unnatural thing without another ingredient. And that other ingredient is sort of the geometry of the space we're in. So there's actually this way of sort of putting a geometry, what's known as a metric, on R2, say on the plane. And this gradient is assuming that that metric is a flat metric, Euclidean metric. If you change that geometry, you get a very different kind of formula for the gradient. And the gradient is sensitive to that, very sensitive. So if you're doing some more advanced math, you might start getting that more general notion of the gradient. But I think for now, and for most applications, it's not, you don't have to worry about it. This is the definition. So now let's make a note about something I said earlier this lecture. Let's say I'm interested in taking the directional derivative of F. Well, the theorem above says this, that this is actually equal to the gradient of F dot U. This is actually true in any dimension. Not just 2. For the same reason for the chain. Again, you want to assume that F is differential as a function. That's what I was saying earlier, is that the gradient is actually much more general. It's a much more useful thing. You can certainly calculate directional derivatives with the if you know the gradient. You just dot your unit vector with it. You get your directional derivative. So let's just do a computation just to make sure that we're understanding the basics. Let's find the gradient of the following function. G of x, y, z equals x e to the y natural log of c. Okay. Solution. We're just taking partial derivatives. We know how to do it. We're just assembling them into a vector. We get gx, gy, gz. And we know how to take the derivatives in all of these cases. Here we're just going to get e to the y ln x. Sorry, ln z, pardon me. Ln z. Take the derivative of e to the y, we get e to the y. So this is just going to be g itself, x e to the y ln z. And then finally, we take the derivative of ln z, we get 1 over z, and x e to the y, we sort of treat like a constant. Take the partials with respect to z. You will be asked on the exam next week, find the gradient of a function. I really hope that I see vectors. Okay. This has to be a vector. You want to think of it as a vector. It's most natural. It's not expressible as other things. Sure, you can write down the components, but you want to assemble them into a vector. Okay. So one way of thinking about this, right, is you think about three-dimensional space, and we'll talk about this later as well. And you think about every single point in three-dimensional space, you put a vector, the gradient. This gives you some, like, space that's got, is very fuzzy, has arrows pointing every different direction. This is called a vector field. That vector field sort of can dictate in some cases, what kind of force is at a certain point in space, how a fluid is moving through space, all of that. So you want to think of this as this type of kind of larger object, not just individual functions. All right. So why is it so important? If we see it in all kinds of applications, what are the fundamental mathematical properties that make this such a useful thing? Well, one property is what happens when the gradient is 0. So if the gradient of a function at a point AB equals 0, then by that formula we had, and assuming f is differentiable, we know that the directional derivatives of everything at that point is equal to 0 for all unit vectors. But what does it mean when you take a directional derivative, you're really thinking of sort of moving along a line and looking at the function over that line. What does it mean when you have the derivative of a one variable function to be 0? What is that? What do you call that? It's critical you know this. Sorry. Huh? What is it? Critical point, right. So it's a critical point. And so I love the moan of like discontent. All right, sorry. Yeah, I have. All right. So this is saying the gradient is 0 will give us a new notion, many variables of critical point. So here, and we'll talk about critical points next week. We say, not CE, we say that F, or that AB is a critical point of F. And just like in one variable, if you want to extremize a function, namely find its maxima and minima, or local maxima or local minima, you look for critical points. Of course, that's a very useful thing to be able to do if you have a model, find such maximum. So the gradient tells us that, or at least solving equations with the gradient. Gradient helps us with that. If the gradient is, however, is non-zero, and now I want to make sure that everybody knows what I'm saying here. This 0 is not a number. It's a vector. It's the 0 vector. So when I say it's equal to 0, gradient is a vector. So that means that both components are 0 in this case, or all components in higher dimension. If it's non-zero, then this first partial du of f AB is maximized with respect to, I'm going to be WRT with respect to U when U points in the same direction as the gradient. Namely, when U is the gradient normalized, when U is that unit vector normalizing the gradient. Why is that true? Well, what is this? That, by what we had in this theorem, is the gradient of F dot U. And now, you all remember, that's equal to the lengths of these times cosine of theta. Right? Everyone remembers that? One of my favorite formulas? One of your favorite formulas? Good. Everyone's favorite formula. What is this? 1, the loneliest number. So as I vary my unit vector, as I vary the different directions I'm going, what's going to give me the largest directional derivative? Well, what can cosine of theta be? It has to be stuck between -1 and 1. So the largest possible value I can get is when this is 1, which happens when theta is 0, i.e. when U points exactly in the same direction as the gradient. Make sense? Who cares? Who cares? Why do you care? Well, let's say you're making a model, and your model is a continuous model. Your X, Y, and maybe Z, whatever, are the amount of money you want to put into different stocks. And your model's output is how much money it'll be worth. You have a certain allocation in stocks. You would like to change that allocation. How do you change it to maximize your profit? What is the balancing of the different stocks? How much do you sell of stock X? How much do you buy stock X? You only have a certain amount of money to change. You want to choose the direction that will maximize that profit. But of course, this is just, you could do an analogy that's not so capitalistic if you are not of that persuasion. You could say, what's the direction of steepest ascent? If I imagine this being the height of a mountain, the gradient gives you that. So this is why, one of the reasons the gradient is so extremely useful and so ubiquitous in applications, is it tells you sort of this, which direction to go if you want to maximize sort of the rate of change of your function. And it does it very easily, just this simple calculation of partial derivatives. So we can do the same kind of thing, same kind of argument, but if we don't want to maximize it, we want to minimize, then we have to go the opposite direction. And that's because when you're going at, when theta is pi, namely it points directly opposite, this will be -1, and that will give you the steepest descent, as you say. All right, so this is the main, one thing I want is, certainly I'll ask you to make a computation, find the gradient of a particular scalar function, but I really want you to know that these properties, like these properties are quite important application. One final property, which is also very useful, is if the gradient of our function of f is non-zero, then it is normal to the level surface. I'll just say the level set because I don't want to be dimension biased here of f. This is actually very helpful for us. Okay, let me get, so why is this helpful? So we talked about and have talked about if we take a function and take a graph, sorry about this, take a function and take a graph of that function, how to get the equation for a tangent plane to that graph. However, there are we've also talked about a lot of different ways of describing subspaces that aren't graphs, that are given implicitly, not given parametrically. So what 4 is saying is that if we want tangent spaces to things given implicitly, namely level sets, we can find normal vectors using the gradient. Let me give you a sketch of what that means, of why that is. So let's say we're in 2 dimensions and we have a function f of 2 variables. So we can draw the level curves of f. So let's say we draw a few different colors. So let's say this is f at value 0, 1, 2. Let's say these level sets, this is like a contour graph, and we're drawing the level sets. Now, if we're at this particular point, say A, B, then what we know is that the direction that we want to go to maximize the rate of change is the gradient of f. So if I take the gradient of f at AB, which direction should it point? Well, let's say I didn't quite give you everything. So let's say we have another curve down here and it's -1. Well, the direction we should be pointing in then for this is really this way. We should be going up. We shouldn't sort of be going along, the 0 contour, because then we're not really maximizing our rate of change. We should be going perpendicular, really, to this. But that's just saying that when we look at this tangent line here to this guy, that we have a right angle. So this guy is going to be normal to the tangent line. Sorry, this gradient is going to be normal to the tangent line. But of course, we know if we're looking for, say, planes in 3 space, what we need is a point and a normal vector. So let's do a problem using this fact. So let's find the equation for the tangent plane to the hyperboloid given by the equation, sort of the standard one we've looked at before, x squared plus y squared minus 1 equaling z squared. And we need, of course, a point. So let's say at the point 2, 2, minus 3. Well, let's just make sure that everything is right here. If we take 2 for x, we get 4. Take 2 for y, we get 4. 4 plus 4 minus 1. That doesn't look right. 4 plus 4 minus 1 is 8 minus 1, that's 7. I should have plus 1 then. There we go. 4 plus 4 minus 1. I think it did look off. Equals 9, which is minus 3 squared. Good. So we do want, if we have an equation, so it's good to check these things, but if we have an equation, we are going to be finding tangent planes for points that are satisfying the equation. So this equation is a level set of a function. So this is a level surface. Sorry. This is the level surface. For the function, for let's call it f, x, y, z, equaling just x squared plus y squared minus z squared plus 1. And the level surface is 0. Just set this equal to 0, we get a level surface. So what was said in part 4 is that if the gradient of f of this function is non-zero, then it's going to be, that gradient vector is going to be normal to the surface, to this level surface at this point, evaluating the gradient of that. So let's find the gradient. The gradient of f is quite easy. We're just going to take partial derivatives of x, y, and z. We get 2x, 2y, minus 2z. And we evaluate this at 2, 2, minus 3. So let's evaluate at 2, 2, minus 3. This is equal to 4, 4, 6. This is a normal vector. Now, if it's a normal vector to the surface, it's a normal vector to the tangent plane of the surface at that point. But we have the point. It's here. We have the point, we have the normal vector, we can write the equation. And we can, I don't know how you guys like it most, but I'll just write it this way. You take x minus 2, y minus 2, z minus negative 3 or plus 3. This should equal 0. And expanding out, you could certainly divide this normal vector by 2 if you wanted. May simplify it a little bit, but okay, I didn't. So let me write it out. 4x plus 4y plus 6z minus 8. Minus 8. I'm just putting all the constants on the right. It's all equals 0. Plus 18 is going to be equal to 4x plus 4y plus 3z plus 2. And so then we could divide 6 here. We can divide everything by 2 and subtract, and we'll get 2x plus 2y plus 3z equals minus 1. That's our solution. Questions? You can check that the way we got tangent, the equation for a tangent plane to a graph, you can also use the gradient to writing the graph as a level surface to obtain it that way as well, using the gradient. All right, I'll see you on Tuesday.